Hello and welcome to the second part of the FIO Controller 111 tutorial. My name is Volker Marx from Kendrion, and I will show you how to configure the options discussed in part 1 in CODESYS. We recommend using the same version of CODESYS as the runtime version of the controller. You can find information about the CODESYS runtime system of the 111 in the web browser by simply entering the controller's IP address. The default IP address is 192.168.0.111. The password in the factory settings is the printed serial number, and after logging in, you will immediately be prompted to change the password. In this dialog, please enter the serial number again and then assign a new password. Check password. Change password. And we are in the web browser. Under the CODESYS tab, you will find the version of the runtime system, which is 3.5.16.40 here. So let's start this version of the CODESYS development environment. Before we start programming, we need to install the device description and system libraries. For this, on our website, there is a package available in the download section that you can install in CODESYS 3.5.16.40 via the CODESYS Package Manager. Tools, Package Manager, Install, and install the downloaded package. For a higher version of CODESYS, please use the CODESYS installer. Now let's start with a new project. Choose a standard project and select the FIO Controller 111 as the device. Under the internal I/Os, you will find 9 slots, with each slot containing a module. If you are not familiar with the terms slot and module, here's a brief overview. And PLC or EtherCAT slaves can have slots. A slot is nothing more than a software slot where you can plug in different modules. The 111 has 9 slots, of which 4 are shown here as an example. For each slot, there is a selection of possible modules that can be exchanged depending on the application. A module always has a specific function, and you can only plug in one module in each slot. For example, let's plug in the digital input module into slot 3. By plug, of course, we mean configuring. Slot 3 corresponds to the left pin 6 of the connector strip, where a digital input can be connected. If we plug in the analog input module into slot 3, then an analog sensor, either current or voltage, can be connected to the identical pin. A module may also have parameters that configure basic properties of the contained function. For example, with the analog module, a PT1 filter can be parameterized. In slot 4, let's plug in a digital module. Slot 6 occupies 3 pins. In addition to digital inputs, an encoder function, or the end positions and reference switches for a PTO interface can be configured there. We opt for the PTO interface. Slot 7 offers modules for digital outputs as well as modules for a frequency generator, PWM, and the outputs for controlling a PTO interface. Since we have a PTO axis, we use the module for the PTO outputs. But now to the practical part. We find 9 slots under the internal I/Os of the controller with modules already plugged in by default. To plug in another module, right-click on the first slot and then click on Plug Device. For slot 1, there's only one module, Analog Outputs. We leave the Plug Device dialog open and simply click on slot 2 in the tree on the left. Again, there's only one module, Analog Inputs. For slot 3, there are now 2 modules. So you have the option to decide whether the physical input should be analog or digital. The same goes for slot 4. Now come the slightly more complex slots. Slot 5 has 3 modules: digital inputs, encoders, and PTO inputs used in conjunction with the motion library. We'll cover that later. Slot 6 has the same modules as slot 5. Slot 7 even has 4 modules. In addition to digital outputs, there's a frequency generator, outputs for direction and stages, and PWM outputs. Slot 8 is identical to slot 7, and slot 9 has a module for digital outputs. However, the selected modules also have specific properties or parameters that affect their behavior. You can always find these parameters depending on the module plugged in by clicking on the slot and then on the internal parameters card. The first module serves as an analog output, and here we see that there are two outputs: analog output 01 and analog output 02. In the value column, these can now be switched from current to voltage. We select 0 to 10 volts for the first analog output and 4 to 20 milliamperes for the second analog output. Now we move to slot 6 and plug in the encoder module. Plug device. Encoder. Here, among the parameters, we see the option to set the edge for referencing, rising or falling edge, or both. But where do we find the variables of the individual modules? So where exactly is their process image? Well, now it gets a little tricky because depending on the module, the process image is located in different places. Let's take slot 5, for example. The digital inputs module is plugged in there. Since each input also has parameters, we see that inputs 2, 3, and 4 belong to this module. For digital or analog modules, the process image is always located in the respective I/O mapping of the slot. And there, under Kendrion, internal I/O mapping. These inputs can be assigned variable names here for use in the program. Here we have DI2, DI3, and DI4. When it comes to analog values, it's different. Long live the variety. Here, the process image resides in the respective I/O mapping of the slots. Let's take slot 2, for example. The analog inputs module is plugged in there. Since analog modules also have parameters, such as options for current, voltage, and filters, we see that analog outputs 1 and 3 belong to this module. The process image of the analog values can always be found in the internal I/O mappings of the respective slots. Here, variable names can also be entered. We need AI1 and AI3. Now let's move on to modules with functions other than purely digital or analog, and let's exclude all PTO modules for now. Even with these modules, the process image resides in the respective I/O mapping of the slots. For example, if we configure the encoder module in slot 5, plug device, encoder, we'll find, in the I/O mapping, variables for position, velocity, status, or configuration. In our program, we need the position. Or if we use the frequency generator module in slot 7, the variables are also located in the I/O mapping of the slot. In our program, we need the output frequency. But which physical pins belong to a module? A look into our manual will help. You can find the link below the tutorial. There, in the Module Connector chapter, you'll find an overview of slots, modules, and pins. Here's a small example. If you've configured the digital inputs module in slot 6, then DI06, DI07, and DI08 belong to it. These can be found on the right side of the front connector at pins 8, 9, and 10. Now let's talk about PTO, which stands for Pulse Train Output, the control of motor output stages with pulse and direction inputs. The 111 can operate 2 of these output stages. In addition to controlling pulse and direction, inputs for end limit switches and the reference input can also be configured. For axis 1, we find the PTO modules in slot 5 and 7, and for axis 2 in slot 6 and 8. Here we configure axis 1 and insert the PTO inputs module into slot 5. PTO inputs, plug device. Looking at the internal parameters card, we see that inputs DI02, DI03, and DI04 are associated with this. Referring to the manual, we learn that DI02 is the negative limit switch, DI03 is the positive limit switch, and DI04 is the reference input. The function of these inputs is pre-configured, and we can choose whether the input is low or high active. If one of these inputs is not needed, we select the digital input value here, providing maximum flexibility. The input filter time can also be adjusted here. But we'll leave everything as is and switch to slot 7. There, we insert the pulse train output module. Plug device. Pulse train output. Under internal parameters, we can now configure the behavior of the PTO function, such as reactions to reaching a limit switch or encountering an error, direction of rotation, quick stop options, homing settings, and ramps. Referring to the manual, we find that the pulse output is on the left pin 11 and the direction output is on the left pin 12. The first axis is now configured, and it's time to proceed with programming. As mentioned earlier, with the package for the 111, you've also installed the motion library for the PTO function. Let's load this into our project first. We switch to the Library Manager, Add Library, and search for PTO. Then we load the KICS PTO Controller 111 library. In the libraries per order, we can see an overview of the contained blocks. There are blocks for axis movement, referencing, reading status information, and much more. For detailed information, please refer to the manual. The MC init axis block now holds special importance as it's mandatory for communication with other blocks. It passes a pointer to an axis structure, the process image pointer, and the used inputs for limit switches and ref. We switch to the PLC PRG block and first declare an axis of type axis ref. This is a structure containing all variables related to an axis, found in the library as axis ref. We name the first axis axis 1. Press F2 for the assistant and search for axis ref in the text search. Since there might be other motion libraries using axis ref, we include the structure with namespace. For an initial test, we need the following block instances. MC init axis, as mentioned earlier, needed for each axis. Then we add a power block to turn the axis on, read status to get an overview of the axis status, a jog block for manual operation, and a reset block to clear errors. Now we call the instances using the input assistant. F2, instance call. The first block is init. The first variable is the axis, axis 1 in this case. Then follow the two variables for the process image of the respective axis, RxPDO for output process image and TXPDO for input process image. The process image for the axis is found in slot 8 under internal I/O mapping. The status word is the first variable in the input mapping, named status 01. The control word is the first variable in the output mapping, named control 01. Now we can enter these names into the init block. Since these are pointers, we use the address operator. So address control 01 for RxPDO and address status 01 for TXPDO. Limit switches and ref inputs are optional and only need to be populated if they need to be displayed in the MC read status block. Since we want to display the inputs, we switch to the process image, found like all digital inputs under the internal I/Os of the 111. Here, we name the inputs for the limit switches and the ref switch as LS left, LS right, and ref. Back in the PLC PRG block, we enter these names into our init block. Then we add the instances of the other blocks. Since we operate these with the visualization templates from the library, we only need to enter the axis, here axis. First, the power block, then status, jog, And finally, the reset block. With the visualizations from the library, we can now test the axis. First, we create a visualization. Add object, visualization, and select the MC Power visualization from the KICS PTO group. Link this with the power block from PLC PRG. Following the same principle, we add the other visualizations: MC Read Status, MC Jog, and MC Reset. That's fortunately all the programming we need to do. We log in and then, using the power visualization, switch the axis to the ready state. First, we want to move the axis in the positive direction, so we press jog forward. Nothing happens. Well, not exactly nothing, because in the status block we see an axis error, hex 6200, and in plain text below it says it's an invalid drive command due to the limit switch. Since we've set the option low for the limit switches, we need to first set the input for the positive limit switch to 24 volts. Done. Now press reset once to clear the error, then jog forward, and it's done. The axis moves. We've reached the end of this tutorial, and everything else regarding the programming of the PTO interface can be found in our manual. I hope I've been able to provide you with a closer look at the configuration and programming of the FIO Controller 111, and I wish you success in programming our multifunctional I/O interface.